Hello all, let's start section 6.4, derivatives of logarithmic functions. In 6.3, I explained to you that logarithmic functions are the inverse functions of exponential. It means if you have y equal ln x, it's the inverse of e to the power of y equal x. Today, we will discuss the derivative of some of the logarithmic functions, and I'll start with the derivative of ln x. It means your first formula to remember, number one, is d over dx, or the derivative of ln x. What is the derivative of ln x? The derivative of ln x always gives you 1 over x. That's the formula that you have to memorize and remember to use. But now I'll show you why the derivative of ln x is 1 over x. I'll do a quick proof here. Again, you are not required to learn the proofs, but for those of you that you are interested in why the derivative of ln x, or d over dx, dx of ln x is 1 over x, I'll show you the proof, right? Let's take this equation, which we have e to the y equal x. This exponential equation, e to the y equals ln x. And let's differentiate this equation implicitly. In respect to x. In calculus 1, you learned how to differentiate a function implicitly. I will use that method to prove that d dx of ln x is 1 over x. Our equation is e to the y equal x. Let's take the derivative of both sides in respect to x. Then d over dx of e to the y equals d over dx of x. Correct? d over dx of e to the y is e to the y dy dx, or in some notations, maybe you saw it e to the y prime. Y prime means dy dx, correct? And d dx of x gives you 1. Now, let's solve this equation for dy dx, which means y prime, which notation you use, y prime or dy dx is the same, right? Let's solve this equation for dy dx. To solve this equation for dy dx, you have to remove e to the y from this side. To remove e to the y from this side, I will multiply both sides by 1 over e to the y. Here times 1 over e to the y. After you multiply, these two cancels out. Dy dx equals 1 over e to the y. Remember, when we start with to prove this, I write this equation for you. E to the y is equal x, right? The value of e to the y is x. Let's substitute the value of e to the y here, or replace e to the y with x. Then you can write dy dx equals 1 over x. What is actually dy dx? Dy dx is actually d over dx of ln x. then you prove that d over dx of ln x is 1 over x. We prove that the derivative of ln x is always 1 over x. Please do not be confused, because it will happen later that I will ask, what is the derivative ddx of 1 over x? Immediately students are saying ln x. No, we only know the derivative of ln x, which is 1 over x. Now, when you solve problems, usually, sometimes you deal with 1 over x or ln x, but sometimes they give you a problem like this. Find the derivative of ln of x squared plus 1. Here you cannot apply immediately this formula because here you don't have an x. Actually, your x is another function. You have the ln of a function, correct? Now, I'll give you another formula, which I'll name it number 2, maybe, d over dx of ln u. Let's call it u. Your u is actually g of x. It's another function, correct? What is d dx of ln u? D over dx of ln u equals 1 over u times du dx. Do not forget to multiply it with the derivative of inside. We use this one actually a lot. Sometimes when I see ln x, immediately I'll change it to 1 over x. But if I have ln of x squared plus 1, then I will apply this rule. I can write this rule in a different way also for you. D over dx of, if I have ln u, actually this one equals to g prime of x over g of x. These two formulas, or let's say here, bring a little bit change also. Let's put here also ln g of x. These two formulas are actually the same, right? D dx of ln, let's say g of x. Ln of g of x. Both of them are the same. If you use this one or this one, it doesn't matter because your u represents g of x, right? Your u is g of x. Then du dx is actually g prime of x. If you use this one, for some of you, maybe it's easy to go this way, or for some of you, maybe it's easy to go this way. Which one you use, it doesn't matter. It's the same, correct? Now, let's practice at least 1 or 2 examples for this formula. Example number 1, differentiate. Y equals ln of x cubed plus 1. Here, x cubed plus 1, it's not just ln x, it's ln u, or ln of g of x, correct? To find y prime equals d over dx of ln of x cubed plus 1. Now I'll use the rule that I just explained for you. My u is x cubed plus 1. Then du over dx will be 3x squared. Now, the formula says y prime equals 1 over u. Let me write the formula here for you because it's the first example. Let's actually put the formula also here. D over dx of ln u equals 1 over u times du over dx. Here you have the pieces, you know how much is u, you know what is du over dx, just replace it in your formula. Then you can say y prime equals 1 over u, what is your u? X cubed plus 1 times du dx. What is your du dx? Your du dx is 3x squared. Let's simplify a little bit. Y prime equals 3x squared over x cubed plus 1, final answer. Great. If you use the second formula, which is, I told you, they are the same, your equation was like this: y equals ln of x cubed plus 1. And the second formula says d over dx of ln of ln g of x ln g of x equals what g prime of x over g of x. Which one you use, it doesn't matter which one you use, your answer will be the same. Look, your g of x is equal x cubed plus 1. G prime x equals 3x squared. Now plug in these two pieces here, it gives you 3x squared over x cubed plus 1, which is your y prime. Which way you go, both of them is the same. Usually we use the first one, we go this way. But you can use the other one. Which one you use out of these two, they are the same. They're the same. The meaning is the same. All right? Let's do another example, one more. Example number 2. Find d over d or d dx of ln sine x. Now, d over dx of ln sine x equals 1 over u. It means 1 over sine x, because your u is sine x. Then du dx, the derivative of sine x is cosine x. Now, 1 over sine x times du dx, which is cosine x, which is equal cosine x over sine x, which gives you cotangent of x. It means the derivative d over dx of ln sine x is actually cotangent x. Examples are really easy if you get the concept. What is the concept? The concept is d dx of ln u is 1 over u times du dx, or g prime x over gx. That's it. Which kind of problem they gives you? It's easy. Let me do another example. This example, besides the rule, you will see that you have to use the chain rule also. Differentiate again. Differentiate. F of x equals square root of ln x. In this example, you see your ln x is the inner function. It's inside. You have a square root outside. Or if you write in exponential notation, actually, you can write this function as a f of x equals ln x to the power of 1/2. You see, ln x is the inner function. As soon as I see this, if I was good in calculus 1, I know I have to apply the chain rule. The chain rule plus the rule that just I learned in calculus 2. Let's apply the chain rule here. Then you can say f prime x equals 1/2 of ln x to the power of negative 1/2. You subtract 1 from exponent, correct? Times the derivative of inside. It means d over dx of ln x, or times the derivative of nr, correct? Now, we are working on this part. We take the derivative of this part and we simplify at the same time this part. F prime x equals 1 over 2 ln x to the power of negative 1/2, I'll send it to the denominator. It becomes ln x to the power of positive 1/2 times, what is the derivative of ln x? We just learned that d over dx of ln x equals 1 over x. Then times 1 over x. Do a little bit of algebra, write in a nice way. F prime x equals 1 over 2. Instead of ln x to the power of 1/2, you can write a square root of ln x times 1 over x. Now multiply. F prime x equals 1 over 2x radical ln x final answer. Correct? I used in this problem the chain rule plus the logarithmic, the derivatives of logarithmic function, or the derivative of ln x. Another example. I'll do different examples for you. D over dx of ln x plus 1 over square root of x minus 2. In this form, if you go immediately to 1 over u times du dx, yes, you can go that way, but you will deal with a complex fraction. You may do a mistake. Let's make it easier for us. That's why we had section 6.3, and you learned that if you have a logarithm in a single form, you can change it to expanded form. Let's use those techniques actually to simplify this problem. You see, I can, instead of ln of x plus 1 over square root of x minus 2, I can do this. I can write d dx of, or the derivative of, it's the quotient rule. To change it to expanded form, it means the ln of numerator, ln of x plus 1 minus ln of denominator, ln of square root of x minus 2. Here, you learn in logarithms. When you have logarithms, you don't keep the square root or the radical form. You change it to exponential notation. Here, I'll change it to exponential notation before I take the derivative of these two, correct? D over dx of ln of x plus 1 minus ln of x minus 2 to the power of 1/2. Now it's really easy. It's really easy. ln u. You are applying your formula in two parts of these problems, the same formula. Even before that, to make it more simplified, can you bring this exponent to the front of ln based on logarithmic rules? It make it more easier for you. Let's do that. D over dx of ln x plus 1 minus 1/2 ln of x minus 2. Now, the derivative of this part minus the derivative of this part. D over dx of ln x plus 1. My problem goes longer because I want to show every single step for you, but you are in calculus too. You can escape some steps if you know what you are doing, right? D dx of the first time, for the first term, minus 1/2 d over dx of ln x minus 2. Apply the rule. D dx of ln x plus 1 is 1 over x plus 1 times the derivative, or times du dx. Du dx of x plus 1 is 1. Let me write even that step for you. 1 over u, it means 1 over x plus 1 times du dx. Your du dx, or the derivative of n side, the derivative of n side is 1. Minus 1/2 d dx of ln x minus 2. It means 1 over x minus 2 times the derivative of n side, which is again 1. Let's simplify. It gives you 1 over x plus 1 minus 1 over 2 times x minus 2. You can keep your problem in this form, or you can simplify it right as a one single fraction. It doesn't matter. Even if you keep your answer in this form, that's the correct answer. These are like 3-4 examples for the first formula, which was what is the derivative of ln x. Now, what is the integral of 1 over x? Our next formula is integral of 1 over x dx. What is the integral of 1 over x dx? For all of you, now it's easy to understand what is the integral of 1 over x. I'm sure your professor in Calculus 1 explained to you that integration is the inverse process of derivatives, right? If I have d over dx of ln x, 1 over x, then the integral of 1 over x will gives me ln x. Then that's our formula. Integral of 1 over x dx is actually ln absolute value of x, because you are dealing with indefinite integral, then plus c. That's another formula to remember to can deal with integrals of functions that they are coming in the form of 1 over x dx, right? Now, let's do an example for this. Example number 1. Find correct to 3 decimal place to 3 decimal place the area of the region under the curve x times y, or xy equal 1, from x equal 1 to x equal 2. As soon as you get a formula of integral, that means you can deal with the area, finding the area. Integral is finding the area, right? Integral means area under the curve. Okay, find the area under this curve. Xy equal 1. Is this a curve? Definitely it's a curve, because if you solve this equation for y, your first step, y equals 1 over x. You will divide both sides by x. Y equal 1 over x, even some of you already know the shape. The shape of y equals 1 over x is a curve like this, right? This is the graph of 1 over x. You remember it from college algebra and your pre-calculus class, calculus 1 class. Now, in this problem, actually they are asking you to find the area of 1 over x under the curve from x equal to 1 to x equal to 2. If this is 1, if it's 2, actually they are asking you to find this area under this curve. To find the area under this curve, area means, area under the curve for me immediately means integral of this function 1 over x, and the limits, the upper limits and lower limits, or the bounds are given from where to where, from 1 to 2. We know that the integral of 1 over x is ln x. From where? From 1 to 2. Now, plug in the upper limit and plug in the lower limit, you will end up with ln of 2 minus ln of 1. ln of 1 is 0. It means your answer is ln 2. And if you check in your calculator, ln 2 is approximately around 0.693. It means the area under the curve 1 over x from 1 to 2 is actually 0.693 units. Correct? Example number 2. Evaluate. Integral of x over x squared plus 1 dx. The only thing that I forgot to put in problem number 1, here you have, whenever you have integral, you have to put dx here. How to deal with this problem? Do you see the derivative of x squared here somewhere in your function? The derivative of x squared is x, and I see it in the numerator. Then what I will do, I will use the substitution rule here, correct? I will name my u. My u is equal actually x squared plus 1. Then du equals 2x dx. And if I solve for x dx, 1/2 of du equals x dx. Very good. You have all the pieces of substitution here. Then you can write this one as an integral of 1 over u, you replace your x dx, which is here, with 1/2 of du. You see, your x dx is actually, your x dx is 1/2 of du. It means times 1/2 of du. Now simplify. 1/2 is a constant. You can pull it out in front of integral. 1/2 integral of 1 over u du. Oh, what is integral of 1 over u? Integral of 1 over u is ln u. Because it's an indefinite integral, then plus what? C. Correct? 1/2 of ln absolute value of u, or ln u. Now, how much is your u? It will be 1/2 ln of absolute value of your u was x squared plus 1 plus c. Because the inside is x squared plus 1, any number that you plug in here in x squared, it becomes a positive number, then you can remove even the absolute value sign. You can write 1/2 ln of x squared plus 1 plus c, final answer. Example 3. Calculate. Integral from 1 to e ln x over x, ln x over x dx. Again, the derivative of ln x is 1 over x. Then I can use the substitution rule. My u will be ln x. Then du, sorry, du, not dy. Then du equals, the derivative of ln x is 1 over x dx. Or you can write this way, du equals dx over x. Now you have the pieces of substitution. Same time, because it's a definite integral, you can change the bounds also, correct? Hopefully your professor explained well for you in calculus 1. When you have a definite integral and you do use substitution, you usually change the lower limit and upper limit, or the lower bound and upper bound also, correct? If I change the lower bound and upper bound, u is equal ln x. When x is equal 1, the lower limit, when x is equal 1, I will plug in 1 here and see how much is u. U equals ln of 1, which gives you what? 0. This 0 will be my new lower limit or lower bound. Also, u equal ln x. When x is equal e, the upper limit, I'll plug in here e. Then u equals ln e, and ln e I know is 1. This will be my upper bound, correct? Now I will do substitution. I will write integral with new bounds. My lower bound was 0, and my upper bound is now 1. 0 to 1. Instead of ln x over x, you can write u and du, because your du covers dx over x, correct? It will be integral from 0 to 1 u du. What is integral of u? Integral of u will be u squared over 2. From where to where? from 0 to 1. Now, plug in the upper bound, plug in the lower bound. It will be 1 squared over 2 minus 0 squared over 2, which gives you 1/2 final answer. Correct? Let's do another example. I don't know which example is this, 4 or 5 example, let's say 4. Integral of tan x dx. I don't know what is the integral of tan x, but easily I can change tan x as a sin x over cosine x based on the trigonometric class that I had before. Tan x I'm sorry, just my computer disconnected from power. I'll start again. I'll share the screen and I'll continue with the example that I just started. Integral of tan x dx. From trigonometric class, we know tan x equals sin x over cosine x. Let's rewrite this problem now as an integral of sin x over cosine x dx. Here again, you use substitution because you definitely know that derivative of cosine x gives you sin x. Then name your u cosine x. Then du equals negative sin x dx. The derivative of cosine x gives you negative sin x. If you solve for sin x dx, then negative du equals sin x dx. Then let's do substitution. Here you can write integral of 1 over u. You replace your sin x dx with negative du. Or you can write negative integral of 1 over u du. What is integral of 1 over u? Integral of 1 over u gives you ln of absolute value of u. Then negative ln absolute value of u. What is your u? Your u was cosine x. Then you can write negative ln of absolute value of cosine x. Correct? Plus c, because it's indefinite integral. Again, we know that negative ln cosine x is actually means ln of absolute value of cosine x to the power of negative 1/2. Correct? If I simplify a little bit, here I can write ln of absolute value of cosine x to the power of negative 1 plus c. Whenever you have a negative exponent, you send it to the denominator. Then you can write this one as a ln of 1 over absolute value of cosine x. 1 over cosine x gives you secant x, right? Then you can write this one as a ln of absolute value of secant x. And still you have plus c in all these steps. What does it mean? It means the integral of tan x dx equals actually ln of absolute value of secant x plus c. You can have this one also as a formula. Sometimes you need to change the integral of tan x. It gives you ln secant x plus c. But later, I will, when I start with the trigonometric functions, you will see all these formulas, correct? Let's start with our new topic, which is general logarithmic and exponential functions. General logarithmic and exponential functions. If you remember, I explained for you, or what does it mean, actual general logarithmic and exponential functions. Here I give you again few formulas that what is the derivative or d dx of if I have log of x base b. What is the derivative of log x base b? The derivative of log x base b is 1 over x ln b. That's my formula that I have to memorize, formula number 1. From where it comes in, I'll do now again a quick proof for you, and you will learn why the derivative of log x base b is ln 1 over x ln b. Let me do the proof for you. Remember the other day we discussed if I have log of x base b, actually this one, we named this formula the change of base, that I can write this as a ln of x over ln of b. Correct? Now, if I take the derivative of both sides, correct, then d over dx of log x base b equals d over dx of, instead of ln x over ln b, can I write the derivative of ln x times 1 over ln b? It's the same thing basically, right? ln x over ln b or ln x times 1 over ln b, it's the same, correct? 1 over ln b, because b is a number, right? It's not a variable. B is a number. 1 over ln b is actually a constant, correct? I can pull it out in front of my derivatives. Then I can write d over dx of log x base b equals 1 over ln b times d dx of ln x. Wow, I already know what is d dx of ln x. And this one equals 1 over ln b times d dx of ln x is 1 over x. Let's multiply these two fractions. Then I can write d over dx of log x base b equals 1 over ln b times x. You can write as a x ln b. This is what I gave you at the beginning as a formula. And here you saw the proof why d dx of log x base b is 1 over x ln b. That's the reason. Right? That's not really a very difficult proof, but again, you are not required to learn the proofs, or if you're majoring in mathematics, or you like math a lot, learn the proofs also. I do some small proofs in this class also for you, sometimes, not all the time. I do some proofs for you. You can learn the proof also. But for you, you're required to memorize or learn this formula, right? You can use it in problems to solve the problems. Let's do now an example. Example number 1. d dx of log 2 plus sine x base 10. Again, remember, in this formula, I gave you just log x base b. But if this x is a function, or if this x is like this, 2 plus sine x, it's a function, then you have to use the u, or let me put, write, even it's not in your book, but I can write this way for you. If you have d over dx of log of u base b, this one equals 1 over u ln b times du dx. Do not forget du dx. Your u is actually g of x. You see here, your u is a g of x. It's 2 plus sine x. It's a function, correct? Then put this one also in your notebook somewhere, because it's not in your book. They just give you as an x, but most of the time you are not just dealing with the x. We give you a function like this. If it's a function like this, then apply this rule. It's basically the same, right? Let's apply our rule. Then I can say d over dx of log base 10 of 2 plus sine x equals 1 over u. My u, your u is actually 2 sine x. Then your du equals, the derivative of sine x is cosine x dx. Correct? Or du, we are dealing with derivative, let's write this way. Du over dx is cosine x, right? Then 1 over, you see in your formula, you have 1 over u. Your u is 2 plus sine x times ln b. How much is your b? Your b is 10. Times du dx. Your du dx is cosine x. Then d over dx of log base 10 of 2 plus sine x equals cosine x over 2 plus sine x ln 10. That will be your final answer. correct? Very easy. The next formula is exponential function with base b. What is the derivative of an exponential function? For example, if you have, let me write for you here. It means if you have f of x equals b to the power of x. What is the derivative of b to the power of x? Correct? The formula says the derivative d over dx of b to the power of x equals b to the power of x ln b. That's your formula. Correct? But from where it comes in, again, I'll do a quick small proof for you. Instead of b, you see, instead of b, based on algebra, can I say actually b equals e to the power of ln b? Remember, when e and ln comes together, I told you they becomes 1. Then e to the ln b is actually b, right? I can write b as a e to the ln b. Now, the derivative of d or d dx of b to the power of x, actually I can write this one as a d dx of, instead of b, I can write e to the power of ln b all to the power of what? X. I'll replace b with e to the ln b. Correct? Now, again, here you see you have to apply the rule, correct? The chain rule. Then this one equals. Chain rule says the derivative of e to the power of ln b to the power of x, the derivative of e is always the same thing. That gives you e to the power of ln b to the power of, let's say this way, x times the derivative of inside. What is the derivative of inside? The derivative of inside, you are looking for the derivative d dx of ln b, which gives you e to the power of ln b x, or all to the power of x, whatever, which way you write, times, what is the derivative of ln b? The derivative of ln b is 1 ln bx. Actually, the derivative of ln bx gives you ln b. Now let's multiply and simplify by the rules, correct? E to the ln b to the power of x, e to the ln b actually was our b, right? We named our b as e to the power of ln b, correct? Let's replace back. Instead of e to the ln b, I can write b to the power of x times ln b. Wow, you proved that. D over dx of b to the power of x is b to the power of x times ln b. But again, you are not required for the proof, correct? Just remember this formula. Let's do an example, a quick example. Example number 1. D dx of 10 to the power of x squared. Your b is 10, right? Let's apply our formula. This one equals. You see your formula, you have b to the power of x, yeah, this function, 10 to the power of x squared, times ln of b. How much is b? 10. Times, because here you have x squared, again you are applying chain rule, the derivative of x squared is what? 2x. Which gives you, if you write it in a nice way, you can write this way, 2x 10 to the power of x squared ln 10, final answer. Correct? The next topic is the integral. Integral of b to the power of x dx is equal b to the power of x over ln b. That's the formula, and definitely plus c. That's the formula when you're looking for the integral of a function to a power or exponential function, right? But here your b should be not equal to 1. Right? For example, let's do an example. Integral from 0 to 5, 2 to the power of x dx. If I apply the rule, the integral of 2 to the power of x gives me 2 to the power of x over ln of b. How much is your b here? Your b is 2 over ln 2. From where to where? From 0 to 5. Correct? Let's plug in the upper limit and lower limit. Then this one equals 2 to the power of 5 over ln 2 minus 2 to the power of 0 over ln 2. Denominators are the same. 2 to the power of 0 gives you 1, right? You can write 2 to the power. 2 to the power of 5 is 32. 32 over ln 2 minus 2 to the power of 0 gives you 1 over ln 2. Denominators are the same. Subtract the numerator. Then you can write this one as a 31 over ln 2, final answer. Very easy. You have to just remember the formula. The formula, integral of b to the power of x equals b to the power of x over ln b. That's the rule. Correct? This was the first part of the lecture in 6.4. Now, a very good rule using logarithms to deal or to differentiate some types of really crazy functions, that if you don't use this technique, if you go by quotient rule or product rule, that problems will become really long and there are many chances of doing a mistake. How to deal with those kind of problems, I'll give you a new topic. Logarithmic differentiation. We learn a method by name logarithmic differentiation. That doesn't mean where I'm using these kind of problems, even before I give you the steps. For example, someone is asking you to differentiate and they give you such a crazy function. Y equals, for example, x to the power of 3/4 square root of x squared plus 1 all over, let's make it more difficult, 3x plus 2 to the power of 5. Look at this function. Look at this function. And they're asking you to differentiate. If you go for the quotient rule, or if you move this one up, if you go to a product rule, I am sure in the first step you will stop and say, no, 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 I'm not dealing with this problem. It's not that easy to deal with this problem. Okay? Now, to find easily the derivative of these types of functions that they're really, really difficult to find the derivative or differentiate these types of functions based on the derivative, simple derivatives rule that you learn in Calc 1, it's impossible. We use logarithmic differentiation, which makes it really, really easy for us. Before going to an example, I give you the steps. How to start with a problem, which steps apply, then easily you can finish the problem. Step 1, let's write here steps. Steps for the logarithmic differentiation. Step 1. Take natural logarithm, take, let's say, ln of both sides. Let me put this one in parentheses, of both sides of an equation. Of course, your equation will be in the form of y equal f of x, right? And use properties of log or logarithm to simplify. That's your step 1. They give you such a function, put ln in both sides. Take the ln of both sides, right? And it means expand the right side, simplify. I will show it in an example for you. Number 2, step 2. Differentiate implicitly with respect to x. Those of you that you have problem with implicit derivatives or differentiate a function implicitly, please review your Calc 1. This method is in your Calc 1 class, right? You have the book, please review it again, because you see I'm using a lot. You are using differentiate implicitly. You should know the meaning, what you are doing, right? Problem number 3, or step 3, sorry, not problem number 3. Solve the resulting equation for dy dx or y prime, whatever you name it, y prime or dy dx. These are the steps to deal with such a function. You can find the derivative of such a function, such a big function, easily by doing this 3 steps. Okay? Let's do some examples. I will put this one for you. After you learn these examples, go find the derivative of this one, correct? As a homework or as a practice. Even you see this one becomes really easy for you. But I'll do examples from your book. Right? Example number 1. Where are my examples? Let's start with this one. Differentiate. Differentiate. Y equals square root of x minus 1 over x to the power of 4 plus 1. They're asking you in this problem to find y prime. Differentiate. First thing to do, can I write the square root in exponential notation? Y equals x minus 1 over x to the power of 4 plus 1 all to the power of 1/2. Now, step 1, take ln from both sides. Ln y equals ln of x minus 1 over x to the power of 4 plus 1 to the power of 1/2. Simplify your right side based on the rules of logarithms. Simplify here means expand it. It's one single logarithm, write it in an expanded form. Then ln y, I'll show you every single step. That's why this problem goes long. Can I rewrite this one as a ln of x minus 1 to the power of 1/2 over x to the power of 4 plus 1 to the power of 1/2? Now, the ln of a quotient, you change it to subtraction to expanded form. Then ln y equals the ln of numerator, ln of x minus 1 to the power of 1/2 minus ln of denominator, ln of x to the power of 4 plus 1 to the power of 1/2. Bring the exponent to the front, then ln y equals 1/2 ln of x minus 1 minus 1/2 x to the power of 4 plus 1. Wow, you see now, oh, wow, the right side is really easy. I know what is the ln of the derivative of ln of x minus 1, correct? If you take now the derivative from both sides. But implicitly, in respect to x, d over dx of ln y equals d over dx of this part, 1/2 of ln x minus 1 minus d dx of 1/2 ln x to the power of 4 plus 1. d dx of ln y gives you 1 over y. Because you are doing implicitly, then you have to keep y prime or dy dx, which notation you use, it doesn't matter. Equals, here 1/2 is a constant, d dx of ln x minus 1, we learned it today, is 1 over x minus 1 times the derivative of n side 1 minus 1/2 the derivative of ln of x to the power of 4 plus 1 gives you 1 over x to the power of 4 plus 1 times the derivative of n side, which is 4x cubed. Let's simplify. 1 over y, let's write instead of dy dx y prime, right? Y prime equals, here becomes 1 over 2 times x minus 1 minus, here becomes 4x. Even you can cancel this 4 with this 2, right? 1 times 2 times, that gives you 2x over x to the power of 4 plus 1. What to do now? Solve for y prime, step 3. To solve for y prime, you have to multiply both sides by y. Multiply this side by y and multiply this side by y. Y cancels out with y. Y prime equals y times 1 over 2 distribute to x minus 1 minus 2x over x to the power of 4 plus 1. Now, how much is y? Just substitute the value of y. Your y is actually the given problem. Your y was a square root of x minus 1 over x to the power of 4 plus 1. Just bring this value here. Y prime equals square root of x minus 1 over x to the power of 4 plus 1 times this parentheses, 1 over 2x minus 1 minus 2x over x to the power of 4 plus 1. Final answer. Do not try to distribute. Right? If it's easy, do it. If not, keep it this way. That's your final answer. 2x cubed. Sorry, not 2x cubed. Because the derivative of here, it gives you 2x cubed. It was under my video there. I couldn't see the cube. It's 2x cubed. Correct? Let's do another example. Differentiate. Y equals x to the power of square root of x. What I do, immediately I'll apply the ln in both sides. Ln y equals ln of x to the power of square root of x. Now, based on the logarithmic rules, this square root of x comes to the front. The ln y equals a square root of x ln x. Instead of a square root of x, you can write x to the power of 1/2, right? You can do that. Ln y equals x to the power of 1/2 ln x. Now, take the derivative implicitly in respect to x, or differentiate implicitly in respect to x. d dx of ln y equals d dx of x to the power of 1/2 ln x. d dx of ln y gives you 1 over y prime, or dy dx, equals, here I shouldn't explain to you at this time. By looking to this in calculus 2, you know that you have to apply the product rule. It's a product rule, correct? X to the power of 1/2 ln x. Your product rule was d over dx of f times g equals f g prime plus g prime f, right? Or f g prime, g f prime, correct? Now, f g prime x to the power of 1/2 g prime, the derivative of ln x is 1 over x, plus g, which is ln x, times f prime. What is the derivative of x to the power of 1/2? It gives you 1/2 x to the power of negative 1/2, right? Let's simplify. 1 over y prime equals, here move this x up, you have x to the power of 1/2 times x to the power of negative 1, correct, to simplify, plus ln x times, here bring the x to the denominator, it gives you 1 over 2 radical x, correct? Or 1 over 2 times x to the power of positive 1/2, which means square root of x. Simplify this part. 1 over y prime equals x to the power of 1/2 times x to the power of negative 1/2 gives you x to the power of negative 1 gives you x to the power of negative 1/2 plus ln x over 2 radical x. This one goes to the denominator to change the positive exponent. 1 over y prime equals 1 over square root of x plus ln x over 2 radical x or square root of x. Last step, multiply both sides by y. Y prime equals y parentheses 1 over square root of x plus ln x over 2 square root of x. Even in this problem, I want to change it to one fraction, correct? Because it's really easy. You see, if I multiply my first fraction with 2, top and bottom, I can write it as a one fraction, correct? Then I can write y prime equals, what was y actually? Your y was x to the power of x times here 2 plus ln x over 2 radical x. Final answer, correct? I will do one more example. Actually, this example is the proof of the formula that you see and you are using it every day when you are dealing with derivatives, when you take the derivative of a function, or we call it the power rule. And calculus 1, maybe your professor didn't show you the proof why it's like this because you didn't know on that time. But right now, in this topic, even you can prove that formula, right? Let's do another example. This example is actually the proof of a formula. Proof of the power rule. Remember, if you have f of x equal x to the power of n, f prime x equals nx to the power of n minus 1, correct? We give you this one as the main rule of derivatives and calc 1. Now I want to prove this for you. Why it becomes nx to the power of n minus 1. This is your function, f of x equals x to the power of n. Can I write this one as a y equal x to the power of n? Definitely yes, right? Let's apply ln. Let's apply our rule. ln y equals ln x to the power of n. Based on the logarithmic rules, n comes to the front, then ln y equals n ln x. Take the derivative of both sides or differentiate implicitly in respect to x. D over dx of ln y equals n. N is a constant, it's a number, it's a power. D dx of ln x. D dx of ln y gives you 1 over y prime equals n. D dx of ln x is 1 over x. Then 1 over y prime equals n over x, correct? Now, so for y prime equals n over x times y. What is y? Your y was x to the power of n, right? We start with this. Let's plug in y here. Then y prime equals n over x times x to the power of n. Let's simplify this part, right? X to the n over x. Or you can write this one, like, to make it simple to understand what you are doing. Keep the n times, you can write this one as a x to the n over x. Let's simplify this part based on the exponential rules. A to the m over a to the n equals a to the m minus n, right? Let's simplify. Then y prime equals n x to the power of n minus 1. You proved it. You proved it. This is the reason. If you have 2x to the power, or let's say only x to the power of 5, you take the derivative, you write 5x to the power of 4. You learn this in calculus 1, you apply this rule. But why? The proof here, you learn it in calculus 2. Correct? This was all about 6.4. I'll stop your lecture here. I will not cover 6.5 for you because I know some of you may study hyperbolic trigonometric functions. And let's see what is 6.5. Your 6.5 is, 6.5 is the exponential growth and decay. I'll jump, and I have a reason why I'm jumping, because when we go to chapter 10 or chapter 9, when we talk about the differential equations, actually these problems comes back there. Then I'll explain it in chapter 9. That's why I'm not touching 6.5. We will escape 6.5, but we will cover it when we go to chapter 9, right? See you next time for lecture 6.6.